All right, so let's talk a little bit more about flooding, which we talked about a second ago. So, hydrographers basically divide the world of floods up into two fundamental types. So, we'll call this floods. And those are flash floods versus slow rise floods. You can imagine what the difference is just by the name, right? So, a flash flood in a hydrograph is going to have this would be time, and this would be Q, right? So a flash flood would have a very rapid rise and generally a very rapid decay. So it's a short amount of time, often with a very high peak. And a slow rise flood is generally a broader, uh, lower event with not as much of a peak and a much longer duration. Um, so let's think for a second again about what sort of characteristics we might expect to have that would produce flash floods versus slow rise floods. So think for a second about the watershed. What sort of watershed characteristics might lead to flash floods, right? So if you want to have a flash flood, you need, when the rain starts falling, you need to funnel that rain as quickly as possible into the stream, right? So what characteristics of a watershed could get the water from the land surface into the stream as fast as possible? I'll give you 10 seconds, and everybody should just sort of brainstorm to themselves some ideas. You can just write them down. What characteristics of the watershed would lead to flash floods? Go ahead and write them down. Okay, so I'm back. Maybe you've come up with this already. Well, if you want the water to get into the stream as fast as possible when it rains, right? You want to get that water down there as fast as possible. Then you want to have steep slopes, of course, so the water runs off faster. You want to make sure that when the water runs across the land surface, it's not impeded by much, so very little vegetation. If water has to run across the land surface and constantly be moving around roots and trees and that sort of thing, it's going to be slowed down. Um, and and then of course you want to have certain characteristics. The other characteristic of the watershed probably is that it's small. If water has to travel for hundreds of miles to get to the river through a series of other streams or whatever, then you're going to have a much slower response. So small watersheds, poorly vegetated, steep slopes are likely to lead to flash floods. And of course, there's something else that we can say, which is about the storm itself. We want a high intensity or sort of a burst of rainfall. The more water that you can get out of the sky onto the land surface in the shortest amount of time, the more likely you are to have the water levels rise way up in the stream valley. Um, so uh, one way to think about the flood response is to think about a couple of different scenarios here, a couple of different characteristics. So imagine that we have the same basin. This would be time, same watershed, and this is stage or Q or whatever, right? And we have a natural, so what we're going to do is I'm going to draw a little bar over here. This little bar represents a pulse of water from time 0 to time 1, whatever, like 1 hour of really, really intensive rain. So in this case, what happens is the rain turns on, it rains intensively for a fixed amount of time, and then just like you're taking a shower, it turns off and the water goes away. So if you were in a natural sort of Midwestern vegetated rolling hill sort of watershed, a natural watershed, what would we expect to see? Well, as soon as it starts to rain, we'd start to see the water level rise, and it would continue to rise for some amount of time after the rain had stopped. And why is that the case? Why is the water level, the discharge in the stream, going to continue to rise even after the rain has stopped? That's right. The answer is that it takes a while for the rain that falls way up on the hills to make its way down across land and into the stream. And so you get a hydrograph that looks something like this. So by and large, you have a relatively low peak, low and broad peak in terms of the discharge. A low and broad peak discharge. If we look at the same rainfall event, though, in an area that has been had some roads in it, and maybe it's got some subdivisions, and maybe some of the forest has been cleared down and transformed into fields, row crops, and that sort of thing. Now, when the water hits the ground, it's going to be able to make its way more quickly off of the ground, over the ground, and into the stream. And so what we would see then is the same amount of water is going to be making it to the stream a little bit faster. The peak is going to be higher and shorter. So this would be sort of a semi-developed watershed. And now think about the sort of worst case scenario in terms of flooding. Imagine you're in an urbanized area. Think about what humans have done to their landscape to deal with rainfall and flooding. We don't want rains getting into our house, right? So what do? We build pitched roofs. And when the rain hits the pitched roof, it runs right off because the roof is impermeable. We don't want the water just splashing down off the sides of our roofs, so we put gutters there that collect the water and funnel them and dump all the water out in exactly the same couple of spots onto the land surface. When it hits the land surface, what does it hit? Well, a lot of times it hits sidewalks or parking lots or roads. It's supposed to be a road there. Road, sidewalk, parking lot. And each one of those parking lots is impermeable. Each one of those sidewalks, each one of those roads is more or less impermeable to water. So the water runs off. If it runs off the sidewalk or the road, it goes into storm sewers, which are these underground tunnels that are designed to take the water from where we don't want it, which is on the land surface, in our homes, in our parking lots, in our yards, and get it out of the system as fast as possible. So the storm sewers, which underlie the roads, basically discharge straight to the river, and the water is taken instantly out of the system. Now, when I say it's taken out of the system, it's taken off of the land surface, and it's transferred very, very quickly to the rivers. And so in an urbanized area, we would get a spike maybe that looks much more like this. Okay? So this would be urbanized. What we have done by building parking lots and roads and houses is we've created very, very efficient ways to take water from when it hits the land surface to put it into the river as quickly as possible. And in so doing, we've shortened the amount of time it takes for the water to reach the streams, and therefore we've gone from low, broad peaks to short, high peaks. Now, which of these three scenarios, if you were living in a town on the banks of a river, would you rather deal with? Well, of course, you don't want the water coming up, even if it just stays in your home for half an hour, 10 minutes. You don't want the water coming into your home. You'd much rather have low, long, or prolonged floods. But we've moved as we've urbanized and suburbanized from here to here to here over time. And it's a big problem. So dealing with that, we have come up with a couple of solutions, right? So how do you deal with, or apparent solutions, short-term fixes? How do you deal with that? Well, one thing that you can do, right? So mitigating floods. Mitigating flooding. One possibility is that you remember those natural levees that form on the sides of rivers, right? These sort of natural little bumps. Well, you make them bigger, and you make them bigger, and you make them bigger and bigger still. So you increase the size of levees. And in some cases, these are monstrous. And we'll be reading about that when as you read John McPhee's book. He talks a lot about the levees in the Atchafalaya and the southern Mississippi. So, of course, what that means is the water is required to stay in its banks for longer, um, which also means that if you're downstream, now you've got an even bigger flood coming your way that your levees have to deal with. So there are trade-offs here. Another possibility is to deal with the river itself. So imagine that we have a river that looks like this, nice meandering river. The river is going this way, it's flowing downstream. And let's say that at this point, the elevation is 1,000 feet above sea level. And here the elevation is, let's say, 990 feet above sea level. So the rate at which the water is going to flow down this stream is in part a function of how steep the river is sloping, right? Well, here we're dropping from 1,000 feet above sea level to 990 feet above sea level. So that's a difference of 10 feet in elevation. It's a 10 feet elevation drop between this point and this point. But you remember how you calculate slope. Slope is equal to rise over run. So the rise is 10 feet. What's the run? Well, the run in this case is measured as this distance all the way along this curving riverbed. So maybe it's 1,000 feet if we measure just right down the middle of the channel. So that would be a slope of 0.1 or 1%, right? Well, if we wanted to get the water out of the river system faster, so that it instead of it building up in here and being more likely to flood its banks, what if we wanted to just get it out of the system even faster? Well, what we could do is we could increase the slope. If we increase the slope, the water shoots out of here and is more likely to be evacuated from the system rather than building up and flooding out onto the floodplains. So the way that this has been done in order to increase the slope is you need to shorten the distance between this point and this point. And so what organizations like the Army Corps of Engineers, the U.S. Army Corps of Engineers, and other agencies have done is they've come in and they've literally they've built new channels. They've connected this point, this meander to this meander. That allows the water to flow straight across and allows it to go from 1,000 feet above sea level to 990 feet above sea level in a shorter distance. And as you do that, if you keep the rise the same, but you decrease the run, then the slope has got to increase. If the slope increases, the water is going to flow out of the system faster. So that's kind of interesting, right? Well, it turns out that that nature does that same sort of thing on its own. That streams are very dynamic systems. So remember how streams can be very curvilinear like this, right? They have these big meanders. And remember that in the meanders, if the water is flowing this way, you are eroding on the outside of the meander, right? So eventually what can happen is one meander can actually cut through and connect with another meander so that the water is flowing along like this. This erodes through, and now it goes down here. What's left behind is a river that looks something like this. And the old river channel is abandoned and left hanging out in the floodplain over here. This is called an oxbow lake. In general, the further down a river system you go, the more curvilinear, the more meandering the rivers get. Up in mountains, they tend to be straighter, and down, so something coming out of the Rocky Mountains is more likely to be straight, and down in the Gulf of, or in the Mississippi Delta, down in Louisiana, for example, the rivers tend to have many more meanders, which is kind of interesting. As these meanders are migrating back and forth, one thing to keep in mind is that what you're looking at when you see a river, and again, this is all map view, when you see a river that, I'm going to draw sort of a topographic map here, you'll see contours very steeply sloped here and here and here and here. And the river will be running down the middle like this. So this is the river channel. This is called the floodplain. And then these would be the hills on either side of the floodplain. So remember that the channel is dynamic. So it's constantly eroding over here. It's depositing in here. it's eroding over here, it's depositing over here. And if you were to stand up in space and look down and take a photograph of this river over time, take, say, one photograph a year for 10,000 years, what you'd see would be akin to if you've ever seen somebody who's spraying a high powered hose and they drop it and the hose starts sort of flailing all over the ground and before they can get a hold of it. That's essentially what this river would look like it's doing over time. It's moving back and forth, and as it does that, it's picking up sediment here that's been deposited by the river maybe thousands of years before, transporting a little bit further where maybe it gets deposited here in this point bar and sits for maybe another decades or hundreds of years. So this floodplain, what you can think of when you see these floodplains, it's basically just rocks eroded from some mountain somewhere or some rock somewhere that's being carried down a little bit, deposited, stored there for years, seconds, centuries, who knows how long, before it's finally mobilized by the river again, deposited a little bit further down, carried a little bit further down, and then deposited again. So all of this stuff in here was deposited by the river and then will once again be mobilized by the river. And so it's neat to think that. And I'm going to show you some images and slides here in a minute that illustrate that point. But we'll stop here for now.